I would like to thank you all for our final lecture this year in the Intelligent Infrastructure Thrusts speaker series. We've had quite a variety of speakers, starting with the Director of Research at Microsoft Labs, and we're ending today with a Director of, and it's long so I have to look and I need my glasses, Vice President, Nuclear Power Plant Regulatory Affairs and Standardization for Westinghouse Electric. And we'll hear a talk today about a new generation of nuclear reactors. And the issue of nuclear reactors is important no matter what side you are on politically or anything else. So good knowledge is always the most important thing we can have. Ed Cummins, he's our speaker. His background is from the U.S. Naval Academy. Then he worked or served on a couple of nuclear submarines. He then started working for Westinghouse, working his way up from operations to being in charge of engineering design, and now being in charge of the whole ball of wax for this new family of reactors. So I will now turn the floor over to our speaker, Ed Cummins.
Thank you very much. As he said, my name is Ed Cummins, and we're going to talk about Westinghouse and the Westinghouse AP1000 nuclear plant, which is the plant that we're building in China and the United States. First, maybe a little bit about the company. Westinghouse, as it exists today, is totally a commercial nuclear in the commercial nuclear business, and we are responsible for designing 62 of 104 plants that are operating in the U.S. today. And we design and build pressurized water reactors for the most part. Basically, in the world, there are pressurized water reactors and boiling water reactors, and a few other unique reactors like gas reactors and heavy water reactors. So most of the plants in the world are based on the pressurized water reactor. We have 13,000 employees, $3 billion in annual sales. We're headquartered in Pittsburgh, Pennsylvania. And in this nuclear renaissance has caused us to be growing quite rapidly in the last 2 years. Each year, we have hired 1,300 or so new employees, and we're continuing to hire a little bit less this year, but it'll be 700 or 800 new employees. So we're responding to the needs for resources by hiring both graduates and experienced engineering staff for the most part. That's picture Pittsburgh. Where are we in the world? We're headquartered in Pittsburgh. We have a significant amount of people in Sweden. We bought ASEA Brown Bavaria. We have a fair amount in Connecticut. And we have internationally several places, China, Korea, and so forth. We have actually in San Jose a small engineering office working on some boiling water reactor. So in the Bay Area we have some people. So I'm going to talk a little bit about AP1000. It's a pressurized water design. We've been working on the design of it for about 20 years, a little more than 20 years, which talks about kind of the life cycle of development of something like a nuclear power plant. I'm not sure this is something positive. We talked to some people from the electronic community, and they have a life cycle for a new product of 90 days. So compared to our 20 years, this is a lot. So what's unique about AP1000? The primary thing is that the safety of the plant, for the nuclear safety of the plant, is reliant on passive systems. What do I mean by passive systems? Well, the best definition is that the systems do not require AC power in order to provide their function. That they work on the basis of natural phenomena like density difference, gravity, heat transfer from boiling and condensing. So they work on natural principles, and they don't require AC power. So that has allowed us to simplify. So simplification is probably number 2. And number 3 is modular construction. And modular construction was driven by requirements from our customers to build the plant in a short period of time. So the Department of Energy makes classification of generations of nuclear plant technology. And AP1000 is the first of the Generation 3 plus technology to get a license from the US NRC. We got that license in the end of 2005. And we're seeking actually a revision to the license to resolve some additional engineering activities. So just simply, Generation 1 was sort of the first era of 40 years ago. Generation 2 was what most of the operating plants are in the world. And Generation 3 is generally the new plant designs that the various vendors are supplying today. I kind of implied that at the beginning that the key differences between plants were boiling water or pressurized water. And this slide proposes that there is a much bigger difference between passive plants and active plants than there is between boiling water and pressurized water. And that as we go to the forward, at least in the water reactor business, there's going to be one leg of the tree or one branch of the tree which is based on, I'll say, innovative passive features. And today there are 2 plant designs there, the AP1000 that I'm talking about and a General Electric design called the ESPWR. And on the active side of the plant, all of the vendors have, I'll say, traditional improved plants which provide fairly good safety performance, but they provide the safety performance by adding multiple trains of redundant equipment rather than by trying to simplify the plant design. So I'm suggesting that from a safety standpoint, the modern plants are similar in their evaluation. From a complexity or a difficulty to build and maintain and operate, the passive plants are dramatically different and simpler than the active plants. So in the top bar graph, there's a measure of safety. There's many measures of safety in the nuclear industry, but one of the predominant measures related to probability, and it's basically the probability of having core damage, reactor core damage, in a year of reactor operation. And so these should be 10 to the minus some big number. You can see from the chart that the current operating plants are doing about 5 times 10 to the minus fifth probability of failure from a year of plant operation. And the AP1000 is about 100 times better than that. And from my last graph, the other plants, the active plants that were on the picture, also have similar 100 times better performance in terms of probabilistic safety, but they do so by basically changing from 2 diverse trains of safety to 4 diverse trains of safety, and they add a lot of equipment and pumps and valves and so forth, and they increase the cost of the plant. The bottom graph shows a comparison of AP1000 and a traditional Generation 2 1100 megawatt PWR, and it basically shows that, especially for safety-related components, that we have less than half of the number or volume or quantity that they have in their plants. So this is a simplicity comment. So if you're our customer, what do you want to have in your nuclear plant? Well, our customers tell us that they're in the business of generating electric power. And so they want absolute certainty that the plant that they get built by us will generate electric power on a reliable, certain basis. And typically in the U.S., nuclear plants, the 104 nuclear plants that are operating in the U.S. have an availability or reliability of about 92% per year. So 92% of the time they're generating power. And so our customers want that 92% to be true for any new plant. And the comment that we're making in this slide is that all of the things that are related to generating power in AP1000 are the same technology that they are using on their current plant to generate power for the PWRs. So the fuel is the same, the reactor coolant system is the same, the controls are the same, and the differences really are that for when you need to provide plant safety because of a transient or an event, that the AP1000 uses no AC power and does it in a different way with passive safety systems. And so the net effect of that is that many components that are in current operating plants, and I listed a whole bunch of things which you may appreciate or not, but there's lots of systems and lots of components, exist in AP1000 as, I'll call it, defense in depth or backup safe to the safety systems. But in AP1000, there's no need for them to be safety related because they are really not the primary path for providing safety. So in AP1000, there's no safety-related pumps, there's no safety-related HVAC systems, no safety-related backup electric generation, diesels, so the NRC, when they were, the Nuclear Regulatory Commission, when they were reviewing the design, had a hard time determining what the regulatory basis for these defense in-depth systems would be. And lots of discussion occurred between Westinghouse and the NRC and the rest of the industry. All of our customers were involved in the discussion. And we finally agreed that we would use this probabilistic risk method to determine whether there should be regulatory treatment of these systems or not. And so the NRC said, well, I want you to take this probabilistic risk analysis and make the probability of any of these things, all of these things simultaneously, the probability of them functioning be 0. That means they failed. And with all those things failed, I want you to meet our safety goal, which is 10 to the minus 4th. And so we did this analysis, and we found that the probability for core damage was, for AP1000, with all those things failed, was 10 to the minus 5th, 10 times better. And they finally gave up on regulating these active systems. So this is the plant. Basically, it's a fairly standard pressurized water reactor. All of the safety equipment is in this nuclear island with the containment in here. There's a turbine island, an annex building, a rad waste building, and a diesel building, which provides support. But all of the safety things are in the one nuclear island building, which is simple. The plant is 1,100 megawatts electric, which is about the size of current operating plants, a little bit smaller than the plants running here in California at Diablo Canyon and San Onofre. And this is a plan view. The blue is the turbine building, the green annex building, red is rad waste building. The safety building is the yellow auxiliary building and containment building. We call it Nuclear Island. So I'm going to talk a little bit about some of the systems and some of the design, particularly talking about the innovative designs for the passive safety systems. This has got nothing to do with it. This is what makes the money for our customers. This is the thing that produces electricity. And basically electricity is produced by steam. There's the first device here is a high pressure turbine, and then there are 3 low pressure turbines, and this device separates moisture from the steam so that the low pressure turbines can work. And the last device at the end is the generator. That makes electricity. And that's what the whole purpose of the nuclear plant is, to generate electricity for the grid. So there's nothing, this is very traditional, and there's nothing related in this to nuclear safety. So the reactor coolant system for AP1000 is basically what we call a 2-loop reactor coolant system. There's a primary water circuit, and there's a secondary water circuit in pressurized water reactors. The primary water circuit goes through the core, gets heated up, goes through a heat exchanger, transfers the heat to a secondary water circuit, which boils the water, turns it into steam. The steam goes to a turbine. That steam is condensed and returned to the steam generator or heat exchanger to be boiled again. So there's 2 circuits, and this shows the primary circuit. This is the reactor vessel. The core is in the bottom part of the reactor vessel. I'll show you a picture of the fuel. The fuel is just a heater. All it does is it heats the water. In our case, we don't want the water to boil in the primary circuit, so we have a pressurizer which creates a pressure above the boiling point for the water in the primary circuit. And basically, it's heated in the primary circuit, goes through the hot leg into a heat exchanger with U-tube heat exchanger, basically. That heats the secondary water, which is in here, and boils and comes out as steam out the top. Then the water comes down after it's cooled, and this is a pump, and these are 2 pumps back to the cold leg into the reactor vessel, and repeats the process. This is a picture of the reactor vessel, and basically there's interesting nuclear details about it, but the fuel goes from here to here basically, and it uses fission of uranium, enriched uranium, to cause heat, and that heats the water up and drives the whole system. So this is the fuel. So each one of these, you can see the man standing here. So this is we have in our core 157 of these fuel assemblies, and the fuel assemblies last basically 18 months. A third of the fuel, or a little more than a third of the fuel, is replaced. So the fuel lasts in the core for about 4.5 years. And then new fuel is provided. And the fuel we call it 17 by 17. They're little tiny rods of zirconium that have uranium dioxide pellets in them. And the uranium dioxide pellets cause the heat, and the zirconium provides a boundary that prevents fission products and radioactivity from leaking outside of the fuel. So that's what the fuel looks like. So the passive safety systems, basically in a nuclear plant, probably the biggest issue is that when you turn it off, it doesn't go totally off. That is, if you have a trip of the reactor, the power goes, I'll say, instantaneously from 100% to 6%. And then there's an exponential decay heat curve that the fuel continues to provide power on an exponential basis. It goes fairly fast down to about 1% power, and then fairly slowly from 1% down, never quite to 0. And so with that, you have to keep cooling the fuel, or the fuel will heat up without any heat removal and will ultimately melt. So the biggest challenge is removal of heat from the fuel after it's shut down. The second big concern is that you need to keep water in the core, inventory in the core. And then there's some issues associated with containing the radioactivity of the plant. So how did we accomplish heat removal on a passive basis? I talked about the steam generator here and the normal circuit about between the steam generator and the core. When you trip, the reactor coolant pumps typically turn off also. And so what happens here to remove heat is we have a big tank of water, which is at ambient temperature, 70 degrees or so. And it has a large number of tubes in it, and the tubes are full of reactor coolant water. And so all of this circuit around in the tubes is full of at reactor coolant pressure. And when you open one of these two valves, or both of these valves, basically the cold water in here comes through here, goes through here, goes back up here and through the tubes again. So that you get a circulation, which is based on density difference between water. We call it natural circulation. The dense cold water replaces the hot, less dense water, and you get a flow. And that flow removes the heat from the core, and it starts to heat up this tank of water. And after a while, after a couple hours, actually the big tank of water, 500,000 gallons, the water starts to boil, and the steam comes out this vented tank, and we'll talk about what happens to the steam. We condense it on the containment and return it to the tank. So that after we actuate, just after we open these valves, then without operator action or without anything, the core cooling remains going really forever. I mean, there's nothing that would stop this process, as long as you keep returning some inventory of water to this tank so that it can cool the core. That's a picture of the heat exchanger. It's basically steam generator tube kind of size tubes in a C-shaped bank, and it's full of reactor coolant, and on the outside of the tubes is a big tank of water. So this is a picture of in a scale picture. There's a great big tank of water, and the heat exchanger is shown here. And in this picture, there's shown several other devices. Most of the equipment shown here is designed to keep water in the core. And I had an animation, but it doesn't seem to work without the link to the software. So briefly, I'll say that the first source of water we need to do this passively without pumps. Traditional plants basically have a pump that pumps water into the reactor core. We basically have a tank of water at reactor coolant system temperature, pressure that's higher than the core, that gravity flows into the core and makes up. And then when that gets low, it depressurizes the reactor coolant system, which allows an accumulator to inject. Then it depressurizes more, and it finally allows gravity flow from this vented tank to supply water to the core. So all of that was done by just opening a series of valves. There's no pumps. So you open some valves to actuate each of those tanks individually. That was the animation that didn't work. Containment cooling. The containment function is pretty standard on at least Western reactors. It's basically the safety concept has barriers for release of radioactivity. The first barrier is the cladding on the fuel tube that I showed you, the fuel tube. The second barrier is the reactor coolant system, the reactor vessel, and the rest of the circuit. The third barrier is a containment. In this case, it's a steel pressure vessel, this right here. It's an 1.75-inch steel designed for an internal pressure of 59 psi. And if the radioactivity barriers from the fuel and from the reactor coolant system were to be breached, then the containment holds the radioactivity so that it does not become a hazard to the public. And so in the case of AP1000, we not only use the function of the containment to do a radioactivity barrier, we use it as a heat exchanger. We use this 1.75-inch shell, containment shell, as a heat exchanger. And normally, all the time, it's cooled by air. Air comes in here from the atmosphere, and there's a little baffle which is just designed to get the air velocity right as it heats up. As the air comes along here, as long as temperature inside is warmer than outside, makes it less dense, and ultimately the air goes out the top. So basically a density difference driven airflow. In the case where, for example, you have a break, or you have this tank of water that starts to boil, as I said before, and when this tank of water starts to boil, it heats up the inside of the steel vessel, and at a certain point where it starts to create a pressure in here. Basically, the pressure inside the containment is the saturation pressure of the water that's boiling. And we supplement the air cooling with water from a tank on the roof that comes down on the outside and evaporates when the air comes up. And the energy needed to evaporate is a very good cooling mechanism, because it takes a lot of energy away when you evaporate the water. So basically, the water comes down, and the tank of the water is designed so that with standpipes that basically you can have a high flow at the beginning. You really want the water to flow the same rate the core decay heat goes. So at the beginning you want 6% water, and at the end you want less than 1% water. And if you do standpipes, and after the level comes down, then you have less flow, and then below another standpipe you have less flow. All done passively, so you can control the heat removal from the containment. When the steam condenses on the shell, basically we have a little gutter that returns it to this tank, and that allows the tank to provide core cooling indefinitely. Another animation. All right, so what are the advantages of passive? It's advantages for AP1000, but if you remember my tree branches, other passive plants like the ESPWR work on similar principles, not exactly the same. But basically we have no reliance on AC power. We have no operator action required to have safety. We have an instrument and control system that will automatically actuate those safety systems, and if the operator were asleep, it would still actuate and provide protection. And basically, there's long-term safety assured without any active components, any pumps or any fans. And the containment has high reliability because it's cooled. And we didn't talk about in severe accidents, but basically in severe accidents, if the core were to melt, it would be nice to, I described the 3 barriers, it would be nice to keep the other 2 barriers. And so we flood the outside of the reactor vessel, and it boils, the cooling boils, and basically the core remains in the reactor vessel. We call it in-vessel retention. Okay. So I'm not really going to go through all of this, but if you're going to do an innovative plant design, you have to prove that individually each of the systems work. You have to prove to the regulator, and you have to prove and to yourself, and you have to determine the heat transfer coefficients and show that the systems integrated work together and provide plant safety. So this is a picture of several test. I mean, you can see that this looks like the containment vessel. It's a scale, about 7th scale of a containment vessel, and we had air cooling and water cooling on it. And this is a full height, full pressure, very low scale integral systems test, and this is a 1/4 scale. You can see the bottom of the steam generator and a pump and the reactor vessel. You have a electrically heated rods in there. So you have to do a series of testing to demonstrate that the safety systems work. What is the net effect of all this? And how do you portray it? In a current operating PWR for core cooling and for makeup for brakes, all this equipment is needed. There's tanks and there's redundant pumps and there's heat exchangers and some more redundant pumps and some safety-related diesels. So for the same functionality of that, AP1000 in the containment does that with actually 2 sets of these tanks and this tank and a few valves. So if you want to think about complexity, and in the new pressurized water reactors, this basically is a 2-train system. They've made their systems into 4 trains, so they double the number of pumps and heat exchangers in order to provide the level of safety that is achieved by the AP1000. So it's a question of simplicity. This is a scale model, a scale representation of AP1000 and Sizewell B. Sizewell B is built in the UK, in the United Kingdom, Westinghouse plant design. And it is a 4-train active safety system, PWR, which has a power rating of 1,200 megawatts. And so AP1000 has 1,100 megawatts. So you'd expect the size to be 1211s. But obviously the size is way different than 1211s. And the colors are the safety-related actuation systems. And so in AP1000, you can see all of them are located in this one safety building. And in Sizewell, you have to have water cooling in the end to have where our ultimate heat sink is air. They have to have water cooling, so it's much more complicated, and some data. You know, how much concrete do we have, and how much. We also compared it to Olkiluoto, which is in Finland, which is a different active plant by one of our competitors. So you can see that there really is simplification. The second thing I'd like to talk about, I'm concluding on passive safety systems and simplification, and I'm going to have a discussion on modularization, and I'm going to show pictures of how modularization was implemented in our construction program in China. And so why did we modularize? The driving force for modularizing an AP1000 was we had a very aggressive requirement in the utility requirements document that our customers wrote that said what they wanted when we did a new plant design on the plant schedule for the construction. And they wanted the schedule to be from first safety-related concrete to core load, 3 years. And at the time, this is 20 years ago, we thought that was impossible. And so how could we possibly do it? Well, it's just very difficult to get more and more work done with people working in the same place. You have to do some of the work somewhere else. And you have to bring in parts of the plant already constructed in order to be able to do it in such a short schedule. And so the concept of modularization, you could bring parts of the plant in, build it in a factory in parallel with the construction, bring those completely constructed things and set them into the plant. So we worked hard at this, and especially for those things that were on the critical path to construction, that is, on the longest path of the construction. If you can shorten the critical path, then you can shorten the construction schedule. So we're basically doing open top construction, meaning the roof is open and you put things in, equipment in from the top. And so you need to have access from the top. And you need, for our case, you need a very heavy lift crane. We're talking about 1,000 metric tons. So we have a huge crane, and it has lots of things. Once you have the crane, you might as well build big pieces for it to put in. So you'll see that we have many big pieces that we put in with it. Though even the steam generators, it's probably the heaviest component, weigh 800 tons anyway. So you needed a big crane in order to build the plant, even if you hadn't done modularization. So ideally, the site has barge access, and the modules can be completely built in the shop and then barged to the site and then offloaded. If not, you can build parts of the modules and then assemble the parts of the modules into a complete module at the site. So in the U.S., Shaw, our partner in construction, has built a module factory in Louisiana, and they're just starting to build modules. In China, they built a module factory, and they've built modules, which I'll show you. So this is a total plant construction period. It's 5 years. Basically, the goal that we were trying to make was first concrete to core load being 3 years. And this is the kind of schedule that was in the specification by the customers. So this is an example of a structural module. And this structural module weighs 900 tons. It's basically a interior structure. And the interior structure, what you're seeing here is basically a steel plate on both sides, which is the reinforcement for a reinforced concrete structure. This structure is the primary shield. So around the reactor and the steam generator, you need both a structure and a radiation shield to reduce the radiation from the primary system. And so these walls are about 30 inches thick, and they're filled, after you set this module, they're filled with concrete, and becomes behavior is just like reinforced concrete. The reinforcement is the steel surface plates, and there are little studs, and there's some cross ties, but little studs that hold the concrete to the plate and make the plate part of the reinforcement. So in this one, the steam generators go in the two ends, and the reactor vessel, actually the top of the reactor vessel, is at the bottom of this module, not included in the module. And the pressurizer is in the second little loop. Okay, so you got the concept. I thought maybe the best way to show the impact of modularization was actually show you real construction. We have orders for 4 plants in China, 2 at Haiyang and 2 at Sanmen. Sanmen is the earlier one. Basically, the first construction occurred at the end of March last year, so we've only been building for 1 year. And the schedule says that we'll have fuel loading in May 2013, and operation, that's commercial operation, in November 2013 for Sanmen. And basically this shows a picture of the sites that each of them are designed to have ultimately 6 AP1000s, but we got orders for the first 2 at each site. And here's some just pictures of pieces of the major components. For example, this one, I said that there was a big U-tube heat exchanger for the steam generator. Well, those tubes go through a pressure boundary, and that little drill is drilling through this very thick plate, a place for all the tubes to go through. So the tubes are rolled and welded into this to create a pressure boundary. And this is the pressure boundary, tube sheet we call it, for the steam generator. And the other ones are big forgings that have been machined. Now I'm going to the Sanmen site now, and In the original picture, I showed you the yellow safety-related building of the nuclear island. And this is a picture of the people getting ready to start the construction. We call it, they put a mud mat. And the mud mat means this doesn't have structural significance, but you need some flat surface to put rebar on, and you need some way to keep the water off. And so they pour a mud mat. And they have a rock site, so it's a very, very steep walls around this thing. And so I'm going to show you a sequence of the construction. The first thing they do is put in rebar. And they put in lots of rebar in a nuclear plant. And basically, you'll see, basically the base mat is 6 feet thick. And so you have a big rebar mat a little bit off the bottom, and a big rebar mat a little bit off the top. And then you have little pipes in it for things like floor drains and things, which are needed for your process systems. So this is the base mat rebar. It's a visualization of the base mat rebar. And this is the picture from the top. You look at the top of it, and basically the containment is the big circle, and then the rest of the auxiliary building around. And you can barely see through the top mat of the rebar, and you can see the steep walls from the rock construction at San Min. And the next picture, we're pouring the thing was poured in about a little over 2 days. It's a continuous pour, and basically you can see here they've started at this end, and they're pouring concrete, and they're right here now, and they haven't poured it for this side. And so, as you can see, here's where we started. These are the big pumping concrete, and here they're pouring in the containment. So they're pouring the base mat, and that process takes about 2 days of continuous pouring. And this was March 31st of last year. And so I'm going to show you a picture of about March 31st of this year, and I'm going to say it's a significant difference between the two. And part of the reason is it's a significant difference is because we used modularization. So here's a picture of the bottom of the big crane. I mean, you can see how big it is. That's the bottom of the big crane. We put a few waste tanks, wastewater treatment tanks here. We put them in there because the module that's going to go over them doesn't allow access from the top on them. So the module's going to fit over them. You can see that basically we put steel frames around the containment vessel, and there's I think 12 of these steel frames. And they're going to put rebar along here, and ultimately they're going to pour rebar for the base of the containment. All right, so this is one of the great. You can see everything but the top of the big crane. The big crane is taking a whole part of the fuel transfer system, basically the spent fuel pool, the transfer canal, the cast loading pit, and the rest of the things in the auxiliary building. And it's putting them over the top of these tanks that we have here. And so this whole building, really, it's a whole part of the building. It's 4 stories high. Is one of those steel plate modules that I showed you before, and it has walls, and in a few cases it has places for floors, and in one case where there's no vertical access, we put one of these tanks in here. So the tank, because it didn't have access for it in the future, because it had a floor on top of it, we put the tank in there on the floor, but no concrete in here yet, because it makes it too heavy. And so this gets set down on top of the tanks. And there's a picture of it, actually just lifting it. Whoops. Okay, we're going to talk a little bit about the containment vessel. This 1 inch and 3/4 inch pressure vessel, which is the containment vessel, basically comes in 5 pieces. There's a hemispherical bottom section, and then there's 3 cylindrical sections and a hemispherical top. And so here people are making them, and basically you take plates and you cut them to match, basically, and you weld them together at the site, and then you inspect the welds. And here you can see the people in there. The diameter of the containment vessel is 130 feet. So you can see these little people working in this big pressure vessel. And they're doing things related to inspecting or installing the wells. This is the setup. This is the setup they were working in. It's covered so that they can work outside of the weather. So here they're lifting the bottom hemisphere. And the top part of it's painted because the top part is outside of the concrete. This all will be basically embedded in concrete in the end. And there's little legs that it sits on. And there's little stands that... so that's a big module. Okay, now we're doing the next one here. Here is the bottom head already installed, and we poured concrete to create on the bottom of it. And now they're installing the next piece, which is the support for the reactor vessel. And so this module is shown here being installed, and here it is installed, and it's the support for the reactor vessel. Okay. This next one is ring 1. I mean, I said that there were 3 rings. So after you've done this, you put the next ring on, and then you put the next ring and the next ring and then the top. And so they're going to put this down on here, and then they'll have automatic welders. You got to get the alignment right, but then you have automatic welders that go around it and weld this piece to this piece, and then you repeat it again. So it's ring 1 of the containment. And here it is set. And then this is a module I showed in the original picture, which the steam generator compartment and the pressurizer compartment. This is it being lifted. It's a little over 900 tons. And this is it's in place here now. So you can see that it's sticking way above the ring 1, and so the ring 2 will come up. And it basically is the main part of the interior of the interior structure of the containment. And so you can see that this is March 27th, 2010. So the other picture was March 29th, 2009. So in 1 year, basically, in the back here is that fuel pool structure. The containment structure is already up in the interior part of the containment structure, which is the critical path, is well up. So it's a lot of progress in a single year. And basically it shows the impact of modularization on construction schedule. That's my objective here. One of the things about China is that it will be, the core load in Sinmen will be 2013. The first safety-related concrete in the U.S. is expected, based on licenses, to occur in the fourth quarter of 2011. So there's still a process of licensing review going on in the U.S. In the U.S., just a little bit about Westinghouse. We have 3 signed contracts. They're from South Carolina Electric and Gas, Southern Company in Georgia, and Progress Energy in a site in Florida, and those for 6 reactors. So our total number of plants on order is 10, 4 in China and 6 here. And I'll show you, and this is sort of a sequence of construction. You'll see the first 4 China plants at the beginning of the schedule, which is very good to have lots of lessons learned from them. And then the first U.S. ones in green coming in 2016, commercial operation dates. There was a question on cost. I tried to find somebody other than Westinghouse to say what the cost is, because cost is a sensitive, competitive subject. So various people have said what the costs are of a nuclear plant in terms of cost per kilowatt installed, and it's somewhere between $3,500 and $4,500 per kilowatt. And you'd have to multiply that, for our case, by 1,100 megawatts. So kilowatt and megawatt, there's 1,000 difference. So you're talking $1.5 billion or so for an AP1000. This is a picture just to show you that even though the safety-related construction is starting in the fourth quarter of next year, this is the construction site in Georgia at Vogel. And you can see the existing plant in the background. And basically, they have a problem in Georgia about having very soft soil. And the soft soil is not good for a foundation for a nuclear plant. And so basically, they dug out all the soft soil 90 feet down, so 50 feet below the bottom of the AP1000. And then they're building up by compacting good soil to get a new site. So there's lots of work going on here with these big trucks, either digging or filling the construction in Georgia. So they have about 800 workers there, and they're making good progress. And this one is the South Carolina plant, and they're busy. They have the opposite. They had a hill. They want the hill to be cut off and put the plant on a flat surface for construction. And you can see that here these are circulating water for cooling of the condenser. So these are great big pipes that provide water for cooling the turbine, and they're two-hour supply and two-hour. And so you can see a lot of construction is going on, even though the safety-related construction doesn't start for more than a year. So what about future prospects? I'm going to go quickly through this. There's a bid in at Dominion. There's interest in Czech Republic. They're going to have a bid spec this summer. United Kingdom, India, we need some government permits. China is likely to have the 4 to 10 new plants ordered in the near term. They're going to order it from themselves, if you will. Longer term, there's lots of people. There's second tier in the U.S., which would be enabled by loan guarantees or maybe some environmental legislation. And then lots of other countries have some interest. I had a couple since this was intelligent infrastructure, I just had some thoughts. I didn't know what it was, but I thought, well, how would I apply it to my experience at nuclear plant design? And the first comment I'll make is standardization is essential. I mean, we'll have one plant design for China, the 10 plants we have plus the next 10 or the next whatever number there are. And there's a huge amount of effort in design, and there's a huge value to standardization. Tremendous value. And the customers are recognizing it. They all agree to accept the same configuration. Second, simplicity. And there's basically the passive systems enable efficiency, but there's a culture. The nuclear culture is basically you have a problem like what about a fire, or what about a missile, or what about, and then you make some sort of complicated thing to address that, rather than trying to eliminate whatever the problem is. So there's a whole way to think about design where simplicity makes a big difference. The third one is pay attention to the customer, because they're important. And we had originally a big specification from them, and now we have a group that continually interacts as we finish the design, and they put their input about what they think they want. And we listen to it. But it's interesting because you have several customers. We have maybe, in the U.S., we have 6. We tell them that we can only listen to one voice. So you 6 get together. You decide what you want. When you decide, come talk to us, and then we'll try to implement your desires. We can't deal with you wanting this and you wanting that, because that kills standardization. Modularization the time to market will be very important. It's not essential today in the marketplace, but it will be essential in the future, in my opinion. And if we can, I think we can leverage this modularization to really shorten the nuclear schedule. There's a lot of benefits yet to be achieved on fleet standardization. The spare parts, the training, all the things that the utilities have to do to run their plant. It's really nice that they have 10 other plants exactly like them, that they could take the spare part from the other guy, or that they could borrow a person who was trained in something, an expert. It'll be a tremendous benefit. Then the last comment is maybe, and I really don't intend to go through them all, when they did the utility requirements document, this is 20 years ago, the fathers of the industry made some principles which they said should guide their design. And the next few slides, which I'm not going to go through, but you can just look at the titles, and you can have the presentation show what they said were key. And I think that may apply to, probably applies to more things than nuclear plants. So simplicity, design margin, human factor, that's how does a human interact with the design. Safety, very important for nuclear for sure. This is who owns the margin, the regulator or the operator. Regulatory stabilization, if you keep changing the requirements, you can't ever build something. Standardization, I talked about. Proven, they wanted to make sure that the plant would operate. Maintainability, constructability. Quality assurance, economics. They were already 20 years ago worried about threats. Good neighbor, this is environmental. Make sure that you don't damage the other people. And that's it for my presentation. I guess I can take some questions. So. Thank you.
In the interest of time, that if people have questions, maybe they can come and talk to Ed at the back of the room. So again, we want to thank you and thank everyone for coming to our seminars this year, and we hope to see you back next year.